Good morning, guys. So this is our ME444 design project, and it's a advanced jelly toy, and this is what we have in store for you. My name is Anand.
I'm Julia.
I'm Jadon.
And this is our outline for today. First, let's go down the background story, and we have the exact design, the entire application, and how we can demonstrate that, and we follow with that question and answers. So this is a really interesting and personal story. So as a kid, I always loved lights. So you can see I'm not really that cute, but everyone loves lights. They seem to bedazzle everyone, and I've seen children getting fascinated by them, and they like having stars right here on Earth. And as a child, I always used to love splashing water when I was in the bathtub. It was a daily routine I used to do with my mother. She used to just knock me in the bathtub, and I used to just splash water everywhere. It was hygienic, one, and two, it was a lot of fun every single day. Now, I thought, what if we could have both? Have lights and water, and then have that intricacy and fascination together. So, we came up with this idea, and Beacon Mechanical Engineering gave us the opportunity to use our engineering skills and then make this fantasy actual reality.
Okay, let me introduce our strategy and the design. We aim to make a jellyfish bat toy which is targeted at children of 4 to 6 years old, and because humans are known to visual learners, so it's beneficial to enhance visual and interactive experience of children. And our concept is a floating bathtub toy that is motorized and glows when actuated. We have electric components in the cavity inside the main body, and we have motor and mechanism to make it move like a jellyfish. In the CAD model, we can see that on top we have threads, and we can unscrew the upper body to put the circuit board inside, and we have a motor to drive the bat coupler, and the coupler arm follows the bat coupler to move up and down. It's just like a jellyfish, and it's our prototype. Okay, here goes the demonstration. We can see how it works. Removing details from this section, we can see that there's a motor in the center. The motor will rotate around it like this. So, for instance, this pass coupler rotate. There are slots in the pass coupler with just like a sign of sine curve like this, and there are pins on the slider. So when the pass coupler rotates, the slider will move upside down to bring this out arm move inward and outward, just like this, a jellyfish.
So the second mechanism that we have is the LED light, which works with a circuit board that you can see here. We use some ATT Tiny, and basically there's two main types of motion. You've got two states. So when you put it in the water, there's a water sensor that detects that it's in water, and it'll turn the lights on. And there's a push button where you can go between states. And there's a push button that lets you go between states. So you go between having just the lights on and having the lights and the motor running, which causes, like he said, the tentacles to come in and out. So here's a video of just the circuit, if you want to just play that. That kind of helps explain. So the water sensor's connected, that causes the lights to turn on. It goes through a rainbow sequence. And then when I push the button, it's hard to see, it actually causes the motor shaft to turn or to be stationary. And then here's a video of the LEDs just outside, just so you can kind of see what's going on. And then when I push the button, it causes the tentacles to go in and out like so. And then here's the whole mechanism. When you put the silicone top, it allows the light to be more diffuse, so it actually lights up more uniformly. So we have a demonstration for you guys today. We had to switch batteries at the last minute because the batteries we got actually weren't quite powerful enough for our motor, which is why this is connected the way that it is. So we just put it far enough in the water for the water sensor to detect. Once submerged, as you can see, the lights go on. And then when I press this button, it causes the motor to run, which makes the tentacles move in and out. Sometimes it gets a little bit stuck. Unfortunately, neither of us own a basin that's big enough to show you how it works. So if you want to pull it out, I can't actually, but the way we designed it, we had the ends be flexible and the upper part be rigid so that the water would actually cause the ends to drag and make it go more like this as opposed to just in and out, as you can see it does in the air. So we can't model that because we don't have a container big enough to show you. But it does that a little bit in air, and we are pretty sure that it would do that in water. We just couldn't test that. And then it's got a little Purdue bead on the side because we forgot to mention that.
Questions?
First of all, use of science. But as regards the mechanism, do you see any problems in terms of variability over a period of time?
You mean as in being able to adjust the motion going in and out?
Wear and
Oh,
tear.
as in right there.
Yes. Yes.
We did use Teflon pins, which are low coefficient of friction, and they're more wearable than the actual slot path itself. So if we had made them of the same material, it is possible that it would actually wear out that slot and it wouldn't work as well in the future. So we obviously haven't done any fatigue testing or anything like that, so we're not positive, but since we made it out of a material that chafes more easily than the actual slot itself, it should be able to run for a fairly long time.
And what about weight considerations for buoyancy?
Yeah, so when we originally calculated the buoyancy, it was going to be buoyant with the 3D printed material that they have at Boilermaker Lab, which is what I based all my calculations off of. And then they gave us this like super high quality, really dense stuff. If you can control percent infill and other parameters of the 3D printer, you can make it so that it's got either close to neutral buoyancy or even less. But they don't let us control that because we just send it out or have the FDM do it. And so we weren't able to actually play with those parameters. So when we got it, it was like over twice as dense as we expected. And we tried to do a few things. We drilled out the bottom, for instance, and we're going to stick some foam in here to make it buoyant. But we just didn't have like enough things that we could change since the main body is the majority of the weight, and there was no way we were going to be able to offset that. So we did calculate that, and it was going to work if it was out of the material we expected, but it wasn't, unfortunately.
So I remember that you struggled to make this waterproof.
Mm-hmm.
So how hard is it waterproof?
It's not waterproof right now because I wanted to be able to take this off in case anything went wrong. But there were actually a few features of the design that we didn't have in the end. So if you can actually go back to one of the pictures, the way that we were planning on making it waterproof, do you remember the section view? The way we were originally going to make it waterproof was primarily through a lip seal, which is what's used on things like gearboxes to keep out water. You can see it in here. This is the lip seal. I put it in upside down, but that's what it looks like from a cross-section view. And so that actually basically seals off this compartment so that no water is going to go from the outside into the motor. But the problem is lip seals work based on friction. And so you have to have a relatively powerful motor to actually be able to drive through that lip seal. So in our case, since the motor is barely powerful enough to do what we want, then this wasn't a good motor choice. And so we weren't able to actually make it watertight on the bottom. And if we were to have this be tested to be watertight, we actually would have taken caulking or some kind of like silicone-based material and sealed this so that no water could escape into the compartment. And if it had been printed transparent like we wanted, this lid actually would have been screwed on top, and this push button is what would have activated this push button inside, and I would have just mounted this centrally on the circuit board, and we'd press that, and that would be what actuates the mechanism. But we didn't get a lot of parts the way we expected, so we did design for that. But we didn't have a strong enough motor, and we weren't able to print transparent, so it was kind of redundant to make it more waterproof.